we're reporting now.
Okay. The owl is not track. I need to move.
It's not tracking to you, so if you just kind of
Let me
hook
come this
around.
way.
There you go. Now you're in.
Okay, okay, great. All right. Good afternoon to our people in the room and our people online. It's my pleasure to introduce Professor Helen Reed today. She's coming to us from Texas A&M, and she works specifically in fluids. So it says up here, so stability and transition. And I'm just going to give a brief bit of information about Helen. She's had an incredibly distinguished career, so it's wonderful you're able to visit with us. She's also on our department visiting committee, which is our external advisory board. So okay, I'm going to go, the professorship, is this your preferred one to list? She has several professorships that are in perpetuity. So you're listing yourself here as University Distinguished Professor, also Regents Professor, Presidential Professor for Teaching Excellence, many awards. So she, actually, I met Helen when you were chair of your department and I was an assistant professor, so I've always remembered that. And has done many things since then. Founded her lab, which is a pretty big endeavor at Texas A&M. She's been working with Space Grant for many years, works in CubeSats, or CubeSats or small sats? Well, both satellites, and all around, lots of awards. I mean, I'm not even going to go, there's a long list here. Your bio is in the message that we sent out to everyone, but I'm not going to take up airtime for that. One thing I do want to mention is we're doing this in hybrid mode. So the Q&A is through Slido. So to post questions, go to slido.com. So SLIDO.com, and the code, which I will put up on the whiteboard over here, is 256801. So we just want to have all the questions come in one place so that we can keep it coordinated.
Do we have to do that through here?
Yeah, if you're in the room, you need to do that too, because otherwise it's going to get wonky.
Okay.
Or you could do
During
that.
reception.
I mean, if no questions are coming in, yeah, there's also reception afterwards. Sorry, people online.
That'll be fun.
Okay, well, that I'll turn it over. So she's going to talk about progress in stability and transition research. Thank you so much.
Thank you. Well, thank you so much for having me. It's such a treat to get out of the house, you know, just to go see people, to see some pretty flowers and trees, and it's just been fantastic, and I really, really appreciate the invitation. So today I'm going to talk about this is progress in stability and transition research, specifically activities that I've been working on over the years. So I have to acknowledge the various funding agencies that have supported my work over the years, and they're listed on the first line. I also have had the privilege of working with just an outstanding group of graduate and undergraduate students over my career, and I'm indebted to each and every one of them. You see a picture of the latest crew down here that works on the fluid side, and then all my collaborators and colleagues with whom I've had great interactions over the years. I really appreciate their insights, and I think that has really helped enrich things that I've been able to work on. Okay, so I thought I'd start with, in case there are those that are maybe not familiar with what transition is and stability research, just to get everybody on the same sheet. First of all, the two words in the title are stability and transition. So let's start off with transition. So transition is the process of changing from a laminar to a turbulent flow. And we know that on flight vehicles, on aerodynamics, on systems that we operate in flight, and other applications, the flow will start off from a leading edge, flow left to right. Start off usually will be laminar, and then somewhere downstream, for some reason, the flow turns turbulent. So the transition region, of course, is that region where the flow ceases to be laminar and then ends up going to be turbulent. Now, we know, in looking just from basic fluid mechanics, that if we look at the difference between a laminar velocity profile and a turbulent velocity profile, we see some differences. The laminar skin friction heat transfer rates will typically be maybe on the order of a tenth of those of the corresponding turbulent values, as you can see from the profiles. And these are the slopes of the wall. Moreover, we know that turbulent flow is usually associated with and enhanced mixing, as we see in this cartoon that I've extracted from one of the textbooks. So enhanced mixing can be accomplished for the turbulent flow as opposed to the laminar flow. And also if one is looking out again for waves, other systems, maybe where one is worried about separation or pressure drag, one knows that the fact that the turbulent boundary layer has a higher momentum near the wall, the turbulent boundary layer is going to be able to go through an adverse pressure gradient more easily than a laminar flow is going to be able to do. And of course, the classic example is if one is looking at golf balls, the use of the dimples on the golf ball to incite a turbulent boundary layer means that this separation region back here, this region of high pressure drag, is going to be smaller than that of the corresponding region back here of separation associated with the laminar flow. And these are just simple basics just to get us on the same sheet initially. So we would expect with pressure drag being a lot larger than skin friction drag, we would expect the drag on this configuration to be smaller, overall drag than that, due to the turbulent flow. Okay, so because of the features of laminar versus turbulent flow, we know that transition, in fact, then can critically drive, where the transition occurs on a vehicle, may critically drive the system drag. They enhance the skin friction drag, or the turbulent flow could enhance skin friction drag, or in fact, it could have an effect on a pressure drag. The thermal load, same reasons, we've got the grades at the surface and the enhanced thermal load associated with the turbulent flow. Propulsive efficiency, one would want to go have turbulent flow associated with the propulsion system for the mixing. And of course, vehicle flight dynamics and aerostability themselves are driven by where the flow is transitioning. If you have some asymmetry in where the process is occurring, you can have greater loads on one side of the vehicle than the other, and you will have side loads problems kind of there. The accurate prediction, transition prediction, and efficient control are actually acknowledged as enablers for operations over a wide range of systems, from high altitude UAVs, transports, to underwater vehicles, turbine blades, hypersonics, to ... All kinds of systems depend on knowledge of this process. Okay, I just want to give an example. I like this. This is data from STS, the Space Shuttle 119, after the Columbia problem. So if we look at an example for maneuvering reentry vehicle, we know that heating and drag increase significantly whether one's dealing with a laminar flow or a turbulent flow. In fact, the turbulent rates could be as much as, somewhere they say 5 to 10, so approximately 6 times bigger for turbulent flow rather than a laminar flow. And of course, if you're not expecting these kinds of high heating rates, one could experience substructure failure due to excessive temperatures if transition is occurring earlier or not anticipated to be occurring. And if one wants to guard against this, the way to do it traditionally is, of course, to add shielding, thermal protection systems, or have to design exotic materials to withstand the temperatures. And in adding, the shielding masses, oftentimes is quoted, you'd be experiencing a gross takeoff weight 2 times really what you really might need to do if you've been able to do design more accurately. So this is a picture from STS 119. This is a picture taken from the ground. I believe it's about 50,000 feet. And this was a test where after the Columbia, they were putting the protuberances onto the shuttle to see if they could get data on what would happen if you had something that was equivalent to like a gap filler on the vehicle. So from the ground, this IR imagery is taken, and the blue, of course, is laminar, and the yellows, oranges, reds are signifying turbulent flow. So the experiment was to trip turbulent flow, and in fact, here it is. The data was collected. But then, and it says on here that this was from the flow protuberance. But down here it says this is from turbulent flow from an unknown origin. Okay, so in fact, they also had turbulent flow emanating. I believe it was from the landing gear doors. I think that the turbulent flow to be turbulent down here. So here's some data. The Mach number on the lower axis, temperature in Kelvin on the vertical axis, Mach number on the horizontal axis, and this is heat transfer rate. And these are CFD, computational fluid dynamics simulations coming from NASA Langley. And the measurements, so that the CFD is actually the symbols, L for laminar, T for assuming turbulent, L for laminar, T for assuming turbulent, and the solid lines are actually the flight data that were taken based on measurements. So the computations, if one assumes laminar flow, and so this is coming in, so we're coming in, you see the decreasing amount when we hit the atmosphere. For assuming laminar, this is the trajectory of, this is the prediction of the heating on the surface, the heat temperature of the surface. And if one assumes turbulent, you see it's up here. So again, you can see this multiple effect between laminar and turbulent flow. And you see, in fact, the vehicle comes in, starts off laminar, hits the atmosphere, and then trips to turbulent. And that kind of backs into the predictions. And so you can see we're getting temperatures, in excess of like 1300 Kelvin. So think of some of your classic materials that you'd like to use. And this tells you why you need thermal protection systems or added other kinds of exotic materials and so forth. Coming in here with the heat flux, again, same thing, assuming laminar, this would have been the prediction. Turbulent, here is the prediction. The data follows coming in laminar, you hit the atmosphere, turns turbulent, and you see again this multiple increase between laminar and turbulent flows. This is why we need to have an understanding of whether it flows laminar or turbulent. Okay, the word stability. Stability comes from the following. So receptivity in stability and transition is the process of how free stream turbulence in the environment actually enter into the boundary layer and they interact with surface features, principally roughness usually, and generate the initial disturbances responsible for breakdown of laminar flow. So it's generally accepted that disturbances in flight, disturbances get entrained into the boundary layer, and they create instability waves, stability, okay? So long wavelength sound, free stream turbulence, different scales, they interact with the features of the vehicle, either leading edge, roughness, something. They create shorter wavelength instabilities which lock in and then either grow or decay to go downstream. So these are the instability waves that take a flow from laminar to turbulent. And in fact, if one looks into, this is a flat plate boundary layer simulation a long time ago that was done in Sarah's group. We're looking at the side of a flat plate boundary layer. Okay, going downstream is in this direction. And this is in the normal direction, this distance away from the wall. So it's really like an XY plot. So to see particles in at a point in the boundary layer, it's the computation. Let them go, we get the straight line patterns. See, we start to wrap around, we start to get these kinds of shapes. This is progressing downstream. So we start to get a wavelength, we get frequency, things like that are instability waves. And what's interesting about this is that these particles that are here are for like every 50 particles. You can see as you go down the street, things start to get very stretched out. So if one now looks down on top of a flat plate boundary layer, see what's going on, that's this one. So flows from left to right. So what happens initially is a two-dimensional wave gets set up, like we're doing over here, a two-dimensional wave, and then starts to wrap up and wrap around like it's doing here. So these streaks that we see in a flat plate boundary layer, Pullman-Schlichting waves, are actually modeled by this streak pattern here. So there's a stripe, here would be a stripe, here would be a stripe, another stripe, and so forth. And you can see if it's wrapping around, eventually it's going to break down and you get turbulence downstream. So it's generally accepted that these instabilities, stability analysis, are what are going to cause transition. Okay. So we do a stability analysis. You've seen stability analyses in other disciplines within aerospace. So what we're going to do with the stability analysis is to identify and model relevant physical mechanisms that cause instabilities that could lead to transition to laminar turbulent flow. So to model this is my equation slide. We take a basic state, which is just the flow about which the stability question asks. An undisturbed laminar flow, a flat plate boundary layer, you calculate the CFD, the computational fluid dynamics over an aircraft or a wing or something. That's your basic state, undisturbed. And the question is really good. What small disturbances grow or decay in space or time? These are the ones I want to know about. The ones that grow are going to lead to transition. So the procedure then is to superpose small disturbances onto the basic state and solve. You've seen this in simple dynamics classes, the traditional pendulum. I didn't bring a pendulum, but you would write the equation for that. I can write the equation for that, okay? And then what do? That's your basic state. You put a small disturbance and it decays. Not to let it go, but you know what happens. So I can write the equation for this basic state. Small disturbance on here, you get the picture. That's unstable. Okay. Same thing we're going to do with the fluids. Another simple example is the rotating parallel pipette. Use my laptop case. So you know that about two of these axes, the motion is stable, and the third one is unstable. You can write the equations for this, very, very simple. So about this axis, stable motion, it just rotates and comes back to me. About this axis, stable or unstable? Stable. Okay, so it comes back and just rotates and comes back to me. About this axis? Unstable. So no matter what I do, hopefully it works. I have a lot of junk inside of this thing. Oops. See, it twists in the air. It doesn't stay stable as I'm doing it. It's an unstable motion. You write the equations for this. So we do the same thing with fluids. We're going to write the basic equations, solving for the fluid flow, and on top of that, the perturbations that model these instabilities that I had on the last slide. Okay. So now, let's get into some of the meat of this. So by doing stability analysis, and over the years, a number of unique transition mechanisms have been found. And I think maybe those that are familiar with transition realize that these mechanisms, they can each play a different role in the breakdown. And the mechanisms are governed by that particular basic state and receptivity, meaning what's in the free stream. And these are just a smattering of the kinds of effects that will affect what mechanisms you observe in a process where you're looking for stability and transition. Each one of these causes a different kind of reaction in the boundary layer flow. Okay, whether the flow is 2D or 3D, I'm not going to read them all. Pressure gradient, whether it's favorable or adverse, etc. The list goes on. Particles, I even have particles in here for my colleagues for whom I was talking about particles today. So to reduce uncertainty, prediction has to be based on what mechanisms are present, okay, and the accurate modeling of their evolution in that boundary layer. You can't take one size fits all the transition. You really have to understand the situation in them. Okay, so here's an example of transport, simple transport wing. This is just a simple swept wing. Let's say it's an infinite swept wing, nothing fancy. All right, so transition location mechanisms vary, configuration, conditions, environmental disturbances. We've just established that. So on a transport wing, you can have instability associated just with the leading edge, the swept leading edge. Flow is coming on like this, with a component normal to leading edge and a component parallel to the leading edge. Well, the component parallel to the leading edge is here, and there's an instability associated with this. As it moves along the leading edge, then flows onto the wing. So leading edge contamination, attachment line instability. If you have on the wing, say you have kind of a sharp leading edge, and you want a thicker wing box, so maybe on the pressure side, maybe you have concave curvature. A little concave curvature to go from a thin leading edge, sharp leading edge to a bigger wing box. Concave curvature, that will create Gertler vortices. Now this is an instability associated with going over a concave surface, and you'll end up with counter-rotating vortices, Gertler instability. Okay. In the mid-core region, typically you may have maybe the pressure gradient might not be so might be a zero pressure gradient or slightly adverse or slightly favorable. You would have what are called streamwise instabilities, which mimic kind of what we saw on the flat plate. The flow is in transition by then, and so you might get stretch when the flow is from left to right. A streamwise instability. If you're greater than Mach 1 in the mid-core region, you have a supercritical airflow. Okay, you have supersonic flow. Well, these modes are no longer 2D, now they're 3D. Okay, and if you go high enough in Mach number, you start to get acoustic modes that come in. So a whole rich variety of instabilities that can happen. In the leading edge region where you expect to have a strong favorable gradient, where the flow goes from the attachment line back to the mid-core, That's a 3D bondular. I'll talk about that in a bit. That's associated with what's called cross-flow instability. So you see, you get these, well, again, flow from left to right. This is the leading edge. You get these streaks. Now, these are not counter-rotating, rather now these are co-rotating vortices here. So you get a whole bunch of different kinds of processes depending on the particulars of the flow. And the transient growth, if your roughness is significant enough in the leading edge region, you can get instabilities that are, or growth that's manifested by that. That's a whole other area that feeds into what's going on downstream. Okay, so control. Control you may want to apply for different reasons. First, of course, the delay transition, as we talked about already, fuel efficiency, aerodynamic, heating, load reduction, and long range and endurance. So here's kind of this is the breakdown of a drag budget for a transport. And let's look at maybe laminar flow control effectiveness. And what that means is that where the flow, let's look and see for a typical transport, maybe something in the order of 50% of it can be attributed to skin friction drag. And if we took this little piece right here, let's assume this is all turbulent. If on the wing, for example, if we just laminarize the upper surface to about just back to 50% forward, we would have a savings in drag of about 6.5%. The tail blow surfaces, about 5%, and then sell that about 40%, about 3%. So these are significant changes, significant improvements in the drag if one tries to maintain laminar flow. So control may be applied for another reason, that is to encourage transition. The enhanced mixing or separation delay, such as over control surfaces. Again, you have control surfaces on your wing, and you're expecting back on the adverse gradient ring to flow region where the flow is going to separate. You really would like that flow to be turbulent, so it stays attached. So it covers the control surfaces, flaps, ailerons, whatever, and so that you have control authority. Otherwise, also the inlet of a scramjet engine would be desirable to have turbulent flow, so you want to be sure and be able to encourage your flow to be turbulent to go through transition if you're in that situation. And again, the most effective strategy for control we learned over the years is actually to capitalize on the flow physics. It's not just to go in and put in something through force, but the trick is to identify relevant instability mechanisms and what affects them. We see their whole variety, and modulate the most unstable disturbances as they are just beginning to grow. So just when they're starting to grow is when you have the most effective chance of keeping the flow laminar or encouraging it to be turbulent. And again, each mechanism, of course, like we had on the prior slide, each one responds differently, sometimes oppositely. Okay, let's think about that acoustic mode in supersonics, okay? So the acoustic mode will be destabilized by cooling, whereas the other mode, with that first mode, which was, we talked about with the stripes reaction in 3D, is stabilized. So there can be competing influences, so you have to know what is going on in a situation. So this also applies if we're talking about models and design criteria, even for more realistic tolerances for manufacturing, roughness, and other surface and features and conditions. They also must be based on understanding local instabilities and what affects them. So even if we're looking at these kinds of things, knowing what we're dealing with as far as the basic flow in which these occur is going to be our best chance of coming up with how to model it. So again, progress in identifying the mechanism and sensitivities, because transition is extremely sensitive to given conditions, is made when computations and experiments work together hand in hand, in which validation activities can occur. Okay, so the approach we're taking is our lab, which is the Computational Stability Transition Lab. So I've been working in this for about 4 decades now. And so over the years, and through all this, and things that we've learned, we tried to identify instability mechanisms and complex configurations, try to create and transfer physics-based models, tools, guidelines, and other correlations, including the surface features, and try to help formulate effective control strategies. We had a very, very strong focus on verification and validation, code verification, and validation with working with experiments and with flight tests. And an impact that my student team has had is create a tool set, which we call EPIC, which is based on an advanced stability technique to model various kinds of configurations, from subsonic to hypersonic, We've actually been trying to work to disseminate this to the transition community. Okay, so let me talk about one particular project. We're went fast into this, some of the research we're doing. And this is even either if we're trying to design for laminar flow control or just trying to figure out what's going on with the flow is laminar or turbulent, we do have to worry about the fact that what we're doing in the laboratory is not going to happen in operations. Okay, operational environment can be different. You can attribute it to surface imperfections that are present. There's the 3D features, and you can read them bug stripes that have had paint weathering and so forth, or two-dimensional features. We have control surface interfaces, panel seat, and then manufacturing tolerances. All of these have to factor into any kind of modeling that one is doing. We can learn about the basics from the pristine environment. We also have to take into account we're going to have these other effects. So current practices often take tight tolerances based on fairly general criteria that are available in the literature. We know that if the manufacturing tolerances are too tight, that actually corresponds directly to increased manufacturing costs, complexity, and fabrication time. We know that different features behave differently, so if criteria are based on 2D features, and we're trying to apply it to 3D features, there's going to be some question about that. So if we can get a better understanding of the effects of these imperfections, these excrescences on transition, including pressure gradients, sweep, and so forth, this could be beneficial in actually elucidating strict manufacturing tolerances and allowing significantly more practically producible and maintainable laminar flow rates. So we must quantify the acceptable levels of deviation from laboratory design. So historically, if we're looking at roughnesses and things like that, there's been a quantity called the roughness Reynolds number, based on roughness height and the undisturbed velocity of the height of the excrescence. And the conditions that under which these are created are back these papers that are often created using specific kinds of conditions to create the criteria. And these are used when nothing else is available. Okay, so let me give you a little lesson on swept wings, just to see where a 3D bundler comes from on a swept wing. Okay, that's what I want to focus on. All right, so this is a cartoon of a swept wing, flows from left to right, leading edge, trailing edge, this is its sweep. So as I said earlier, the flow will come on to the leading edge. The component normal to leading edge that comes to rest. And there's an extra component that will run down the wing. So it runs down the wing and it runs up onto the wing. Okay, so if we look at the pressure, assuming a favorable gradient, as most wings have in the leading region. So let's look at the pressure. How does the pressure vary in this direction relative to this line? I would say the pressure here is going to be lower than the pressure is here. Closer to the leading edge, it's going to be higher. So what happens is this streamline tends to deflect inboard toward the root because of that pressure gradient, if you will, in that direction. So the inverse streamline does that. Now, as I go closer to the wall, the flow is less momentum coming to a no slip condition. Closer to the wall, the flow is going to be more influenced by that pressure. So toward the wall, the flow is going to be more pushed inboard because of the higher pressure here and the lower pressure here. Okay? What happens is then we end up in a 3D bonded twisted profile. Twisted bonded profile. That's a 3D profile. So we decompose that into a component in the this streamline direction and a component then perpendicular to that. That component perpendicular will be pointing that way. Okay, so decompose it, necessarily have to be zero at the wall for this cross flow component. It must be zero at the edge, so you necessarily have to have an inflection point. So the cross flow instability gives us an inflection point instability, a dynamic instability. We see when we get something that will be rotated like this, this will give rise to those co-rotating vortices that we see on the swept wing gears. They're pretty much lying in this streamline direction. Co-rotating vortices right around that inflection point. Okay, so we've done a lot of work in swept wings. We've tried to understand the cross-flow instability, but the question is, let's put it into a real application. So what if we have steps in the okay. So as we said, swept wings tend to be dominated by stationary cross-flow instability. We see these streaks. These are those vortices that again, come from wrapping around that inflection point. Okay. So we also know that if we have 2D steps and gaps on the wing, they tend to create recirculation bubbles. Now, most aircraft have 2D standwise steps and gaps. So it could be a leading edge skin panel, a high lift device, anti-icing devices, things like that, can create some sort of a step or a gap in 2D. So the question is, all we've learned about the cross-flow stability, how is that affected by, how does that 2D step, we're calling it an expressance, how does that interact with the established instability? What does it do to it? And then how does one predict step heights associated with early transition? Because we can imagine if we have this pristine flow, we put something like this in here, it might encourage transition to occur earlier than we had predicted with the, just the clean wing configuration. Okay, so we have the crossflow profile coming in. The step has recirculation regions on top and bottom. Okay, so that's what we set off to do. I had the good fortune back at Texas A&M. Sarah had the flight research lab, and in that lab, he had a Cessna 02 aircraft to provide an operational environment for typical transport rental numbers of about 5.5 million per meter. And it's the unit rental number that's critical in matching with real applications. So in the port wing of the Cessna was the model, was the Sweatsley model. And also we have a 5-tunnel plug-on-steric wind tunnel where the unit rental numbers achieved can be 1.6 million per meter. And my husband likes to say, my husband is Bill Sarek, by the way, sorry. He likes to say, well, the tunnel is not as big as it looks here. He just picked the shortest guy on his team. So it looked like it was a really big facility. So anyway, so I had flight and wind tunnel experiments to work with to try to see what would happen in putting a step on the aircraft. I did computational modeling on this. This was a real CFD challenge. So had to model the aircraft with the model. Now we have a variety of scales going on here. Now these excrescences we're talking about are on the order of hundreds of microns. About the boundary layer thickness, your step is going to be in the order of millimeters. The model test port is going to be in the order of meters. The aircraft is tens of meters. And the far field where we have to go for the CFD is going to be hundreds of meters. So all these scales we have to solve. And we know from experience, whenever you're solving these problems for stability, you have to model everything in situ, whether you're putting a model in a wind tunnel, on an aircraft, whether we have to have the whole situation modeled in order to get accurate results. So we did a lot of work to remove features from the aircraft that would not affect the model. And we also had to figure out what to do with this little step. Okay, so what we did with the step was we actually solved for the flow field over the aircraft, including the model of the swept wing. And then we took the boundaries from the aircraft flow field and applied those as edge conditions on a model around the little step itself. And that seemed to work. A lot of work to do that, but that seemed to give us good results. Okay, so from the test, first thing we did was to map out the pressure coefficients. We have 3D pressure coefficient versus fraction of chord on this axis. So the lower ports on the wings, so that was down here about a third of the way up. That's in green. That's the lower ports. The symbols are the experiment, and the solid lines are the computations. This is this label that should say computation. So I doubt if you can read that. Okay. And so the upper ports then coming from pressure distribution method on the upper side here. You see, we get pretty good agreement. We get really good agreement between the computations and the experiment. Okay, so for the steps research, we decided to focus on forward-facing steps. We also did backward-facing steps, but today I'll just talk about the forward-facing steps. The forward-facing steps have two recirculation regions. There's the incoming corner, and then there's on top of the step. So, so I hope you're getting the picture here. So what we're doing is, so on this model, we're actually going to have a step. It's going to run the length of the model. So the cross wind stability is going to come on this thing. And then once the step here, we want to see what happens to the flow field and downstream. Sorry, I should have said that before. So the flow coming into a step. Okay, so the flow is going to come into the step. those are gonna come in this way. So what it's gonna do in the corner region here, it's gonna do this and head toward the tip. Okay, this is the root over here. And on top, it's gonna do the same thing. It's gonna wanna head toward the tip. That's gonna be important. Is that a tendency to wanna head toward the tip. Okay, remember that. The crossflow instability is sitting here in front. Okay, so the experiments, the model was such that they could actually, create a step in flight. So the leading edge just drop down and create a step. They could adjust that in flight. Okay, so what they noticed was small step, nothing happened. Crossflow instability, transition stayed where it was supposed to be. And as soon as they hit critical height, bam, that transition moved forward. This is back when the reference was 15% forward. So this experiment suggested a binary behavior. There was no effect on transition, sudden effect on transition, it slammed forward. It kind of suggested something maybe like a global instability or an absolute instability. We did a lot of work with that based on advanced stability methods, and we just didn't see it. So we decided to go and take another look. So then we got our direct numerical simulation tools out. So we modeled this thing. And we are immediately starting the steps, of course, using the boundary conditions that we got from the flight vehicle, from the vehicle itself. And we're back 15% forward on the wave. Okay, so the first thing we did was do what's called a linear stability analysis. Again, stability analysis to try to see what wavelengths would be most unstable. Right? So fractional chord downstream. This is a length factor is the log of the amplitude ratio. It's the log of an amplitude ratio. How much it's grown from where it is upstream. We'll log that. Okay. So back at 15% forward. Not everything that was unstable. We found that in fact a wavelength of 2.25 millimeters had the largest length factor of this location. And that's what they grew the most. Okay, but the one that was most stable downstream was 4.5. That's this guy. Locally to a 2.25. So we modeled different inflow conditions. We took the most unstable one downstream and the one that was most unstable, or the grown the most locally, and tried them. So what we ended up working with, of course, was the one that ended up being most unstable locally. Okay, let's see what happens. Okay. So once we put the crossflow against an upstream condition on this direct numerical simulation, let it rip. Then we took the flow field downstream and just did some Fourier analysis to see what the disturbances of different wavelengths look like downstream and to see what they were doing. So by examining the evolution of the disturbances, we could monitor how the disturbances were amplified. Okay, so we're 15% forward on the wing, limit for 5.5 millimeter forward run so it's light. Okay, so here's the step. I just have a mark for the check mark. This is distance downstream. So the disturbance comes in, nothing happens. Like this 300 micron step, that's a little blip, and then it continued on its merry way, and nothing really remarkable happened. Go up to 350 microns, and boom, we got this sudden strong growth. Somewhere in between here is the critical reference height. Things didn't happen below that, and things happened above. Okay. So then with that, and look at the disturbances. So this is U and W. U is down the leading edge perpendicular. W is in the spanwise direction. We're taking U squared plus W squared square root. Upstream of the step, we see these profiles for different step heights. These correspond to different step heights. So upstream, no step. And when we get to the step, this will be 150, 150, 300, 350, and 400. Okay, we're just showing how things lifted up. It's normal distance away from the wall where these profiles were measured. Okay, so this is coming in. You see some influence down near the wall as we're getting approaching the step. Then when we get to actually on the step, we see each disturbance is lifted up to its appropriate height. But we see a very, very big difference between the structures when we're below the 300 microns, when we're up above, when we're above 350 and above. Let's less organized to the most highly organized once we get above this critical height. When we look at the vertical component of the velocity away from the wall, same thing. Upstream of the step, we see some effect from V. Downstream, we see what looks like two weaker vortices that may be happening downstream. But as soon as we get that critical height of 350 and above, these organize into one strong vortex. Looks like. Okay. So what's going on? So then now this is looking at the spanwise direction. So the step is happening this way. Okay, so for subcritical, when we're below the 300 microns, we see this kind of disorganization of the V component of the velocity downstream. When we get to the critical height, it's a definite organization into a vortex. Okay. So what's going on? Let's go back and think about, I made this big deal about where things were going. Okay, so as we get on top of the step, the structure is rolling and it's heading to the tip. That's what we're showing here. Heading to the tip, heading that way. Okay? Tip root, tip root. The crossflow instability, which way is it wanting to go? Well, we said that that crossflow component near the wall was wanting to head toward the root because it was getting away from the high pressure and going toward the low pressure. So near the wall, the flow is wanting to go this way, and then it'll wrap back over and then cross a vortex. Crossflow instability is wanting to head that way near the wall and then swing back around like this. Now that inflection point. So here's what I think is going on. I hypothesize that once the step is big enough, in fact, the helix and the crossflow vortex work in the same direction instead of opposing each other. Okay, so if the step is too low, the crossflow vortex is set up here like this. If the step is too low, the flow above the step is heading this way, crossflow is heading that way. It's kind of a destructive pattern that's going on. Once the step is big enough, then the flow on top of the step has been lifted up. So now you're getting constructive effect. Everything now is going to head toward the tip. I think that's what's going on as far as why the critical step height. So we would then hypothesize that the height off the wall of the vortex core corresponds to critical step height, the 2D coordinates step expresses. Okay? Just by looking at the flow physics. And so that would correspond to a maximum of V perturbation. Let's look at that. That's the stability theory. This is the amplification curve. So now we're mapping out, of course, with the stability theory, you get eigensolutions. So now we're mapping the eigensolutions. Of course, the one corresponding to the V is the one that's going to be related to the vortex. Where it's a max, that should be near the core of the vortex. Okay? So what we did then is map out all the V's for all the different disturbances. And if we take the motor shapes now, we go to where the max is off the wall, run this over to our aircraft and to this over here, just away from the wall, and see then that this we would expect then the core of the vortex is going to be this distance away from the wall. So we were guessing that this might be where this critical step height would be in this shape, in this guy right here. And this is just a map of all of these, for all of the inflection points, if we had looked at all the different locations. So there's different ways of looking at it. Is looking at the maximum for the maximum end factor, this would be the 2.25. Which is a little bit bigger, and lower limit would be the most conservative, which would say all the services, where's the V total, where's the V the biggest for all of them. Okay, so let's see how we did. So for that one, we picked off this value here for the V. So this is 330 some microns. That's what it is, 330 or 40 some microns. Put it on the next slide. Okay. Let's see how we did. Okay, so here's the flight. Here's the data. Okay, so unit Reynolds numbers, so the flight conditions are down here. Okay, and Sarah and his team did different correlations, and then came up with a curve. This is what we're following for our prediction. So from what I just said, using linear stability theory, for that particular case, I said 330. Well, this is what we were getting using this linear stability theory, and seeing when the core of the crossover vortex, where its max was, and we're saying, well, maybe that's the critical step height, because then in that case, now everybody's going from root to tip. And here's the data from the flight. It's not too bad. When it's the wind tunnel with similar kinds of results for different unit Reynolds numbers. And these numbers are not too bad to compare this column with these two columns. This is using a maximum amplification of most unstable disturbance level rate. A little bit more conservative estimate for the these numbers are really pretty good. It's much, much better than what was available before, using just 2D based correlations, or maybe down in the 150 to 200 range for microns. So we are continuing on with that work and are trying to apply it to other applications. But what we found from that was the forward-facing steps show larger tolerances than equivalent backward-facing steps in all subsonic studies that we know of. And the height of the approaching station across the vortex appears to correlate well with the critical step height. And that looks like it would be, this is the vortex core height comes from linear stability theory over the plane wing. And it accounts for the integrated picture of pressure gradients, curvature, sweep, wall conditions, and everything. And given that most designs for lateral wings will include performing at least the minimum of a linear stability analysis, it seems like it could be an easily acceptable criteria or accessible criteria providing predictive policy. Okay, so I just want to briefly, with that, I'm going to just change gears and just very, very quickly talk about what we're doing at hypersonics, just for a couple slides, and then I will wrap up. Okay, so in hypersonics, we've been looking at, again, trying to map out instabilities to help the community with predictive capability, in particular for heat transfer rates. And so we started off looking at simple geometries, and you see there are a lot of people working on the same geometry. This was a slender right circular cone. We put it in with pack. The crossflow instability that I just talked about, this would be modeled on this simple shape with hypersonic speeds. So the question is, what's going to be different when we get to hypersonic? This is also the subject of a NATO study that has now been concluded. The publications are out. But we got to look at a whole different set of work together. It was very, very exciting working with the community. Again, these are just some of the things we found. Again, multiple instabilities are present. We even have the acoustic modes coming in. What was really neat was we worked very closely again with Sarah and Alex Craig in the tunnel. So in the tunnel, they were mapping out the crossflow instability. We were getting the same thing computationally, in the same wavelengths, getting the same heights in the boundary layer. That clip up there, I apologize for that. I want to point out this boundary layer is 3 millimeters. Okay, this is 3 millimeters. This is the first data that have been generated in the hypersonic boundary layer details of instability analysis. We got the basic crossflow instability, and then we applied advanced tools that we're also working on to get secondary instability. Because this actual shape of the crossflow itself is creating inflection points both in this direction and in this direction, are leading to secondary instabilities, which break these things down very, very quickly. So our secondary analysis, we're coming in with instabilities on the crest and on the trough, and they match very, very well in frequency and all their properties with what are being observed in the top. So with our tools, we come up with vortex path predictions, because you can imagine going around this cone, it's kind of breathes going around. But the really cool thing is we're seeing a lot of similarities in physics from the high speed to the low speed, especially with these 3D instabilities, in particular the nonlinear effects, and then the subsequent secondary instabilities it gives rise to. Another project that we were working on is the High Power 5. The Air Force, the FRL had a series of sounding rocket programs where they had success articles they were putting on the front of sounding rockets to test different basic fundamental fluid phenomena. And then with the data sets then provided the community to test out the tools. So this was a 2-to-1 elliptic cone, High-Fire 5P was the second launch of it, which was successful. And so just again, with the elliptic cone, again, we were expecting cross-flows, 3D instability, which we've worked very closely with. And with working with the flight team and with the team working in tunnels and things like that, we again successfully were able to identify mechanisms that correspond to instability seen in wind tunnel frequency data. And this is neat, because this is the flight data. So in flight, this is heat transfer rate versus distance downstream. And the dots are for flight. Our calculation shows the heat transfer rate coming down. With nonlinear analysis now, where the nonlinearity starts to kick in, we're picking up the onset of transition with our tools. That's pretty exciting. Down here is amplitude, disturbance amplitude. Again, flows from left to right, obviously. And so looking down on the surface, the dark lines are the laminar regions for us. It's our calculation. And when we start to go with the greens and such, that's where we're predicting the onset of transition. The blue dots are laminar according to flight tests. The red dots are not laminar according to the flight test. We're matching up pretty well with the front as seen from the experiments. We're pretty happy from the flight test. We're pretty happy with that. And then the most recent thing we've been working on is looking at the right circular cone of the fin, and again trying to find the instabilities. This is a work in progress. This is a very, very complicated flow field with these sets of vortices. We have very, very swept leading it from the fins, highly swept leading edges, shock boundary interactions, shock interactions, and all this. We have to try to kind of fit this going on here. So we've been taking our tools, working with the Steve Schneider at Purdue and Comfort Notre Dame and Theophilus in Liverpool. And so far, our group has been successfully able to model the heat streaks we see between computations and experiments, close and right to left. I know it's unphysical, but right to left. And then also we're looking at the different configurations of nose tip and fin configuration study and applying advanced stability tools and having some good success in mapping out the instabilities. So this is just a summary. So over the years, we've learned that the transition knowledge and control, we have to determine what mechanisms are present and the accurate modeling of your evolution in that particular basic state. What mechanisms are present discovered by a particular basic state that can be combined. I have greatly benefited from very, very close collaborations with others. I strongly encourage that for those who are working in this field. And our team, I think, has developed a very promising and predictive tool. We're again actively trying to disseminate to the community, to the transition community for working. And then again, I think we've come up with kind of a new criteria for 4 basic steps based on the physics of the problem, trying to understand the physics and working from there. So these are just some of the challenges that I see for anyone in this field. You could read these. We have the basic states. When we get to more complex geometry, that's a huge thing. It's getting just even the basic states right. Some of the tools even differ as far as that's concerned. We got to come up with low order models and tools for being able to do rapid design. We got to take the effects that we get and distill them down the things that the designers can use. Look at the off design effects. Again, I want to take what we've done for excrescences and take it further. The concept, continue working with others, flight test experiments and collaborations are critical. So with that, I will end and take any questions. Slido, is that right? Slido, whatever Slido.
Yeah, I don't have any questions yet. So can you
Okay.
remind the online people?
Yes.
To,
I did
I
at
guess
the beginning, but I'll do
I will
it
not
now.
force the people.
That's okay. We can, I
We'll let you go real life instead of digital.
Yes,
Go for it.
sure.
So I have a question about validation.
Yeah.
So I don't know how the experimental measurements were made or what you were showing, but can you maybe speak to how how can you compare the simulation results with the experimental results, and how do you go about doing rigorous validation?
The key to working with an experiment is to be able to work like hand in hand, day to day, not just be handed data. You don't want to hand somebody hand you data, you hand somebody data, and then you just try to compare. And I know we have to do like with flight tests and things like that. That's a little different. But if you have the opportunity to work hand in hand, just to go over it and really try to understand what the experiment is make sure that that we're putting the right effects into the simulation. Because what validation means, verification is, are you solving the equations correctly? Validation is, are you solving the correct equations? You just switch the two words. Meaning, do you have all the physics in the problem? So that's the hard part with working with validation, is trying to make sure you've got all the physical effects in there. Because the wind tunnel is the ultimate novice stove talk. I mean, it's right. We just want to be sure we got to understand the initial conditions. So and what the conditions are. You have to get those into the computations. And sometimes it takes a lot of iteration back and forth. If you have effects, if you think effects are important, you can put those in there and see how those change things, what the sensitivities are to those. That's something computations can do, to actually sort through some of the initial conditions and see what effects might be those that would be the sensitive effects. Am I answering your question, or maybe not?
So I was maybe asking maybe a more implementation detail
Okay.
about, so you have some experimental measurements.
Right.
And experimental measurements are limited in some way. The models are also limited in some
Correct.
way. How do you go about actually comparing the results? I mean, for example, I've
Well,
seen
I know.
like
You tried
doing something like bioorthogonal decomposition of the data
Right.
as a way to do some sort
Sure,
of comparison.
sure. Yes.
Is that a
That's-
technique that's
That's certainly a technique that can be applied, yes. The first thing you want to do is you want to try to make sure the basic data is correct. You want to make sure that any level of this is correct. You don't just want to take the final answer and say, oh, yeah, they happen to match. But any part of it that you can, you want to try to match up with. And I've, over the years, particularly working with Sarah, we've gone back and made sure our basic state is right. And then when they decompose and get the shape functions, match up with the shape functions. So I don't just ideally want to match up with frequencies, but I very much like to match up with shapes, measurements in the boundary. So that's why, if I can go back to this one. This was really very, very detailed. The measurements, the number of measurements in here. And we took local profiles and actually saw on the slide with enough space. So we matched the profiles, matched with everything that we could. First thing you have to do is make sure you're measuring in the right direction. That's a huge thing. Because experiments are probably doing in lab coordinates and you're doing something that's body oriented. So you got to make sure, first of all, you got to transform and make sure you're measuring the same things. And then also another thing is you have to make sure you're measuring the same geometry. We had an instance where, not with this one, but looking at just a straight cone, just looking at the acoustic instability. Turned out the wind tunnel model was at a slight 1/10 of a degree angle of attack. And that threw everything off by, tens of kilohertz, 10 kilohertz. So you have to make sure the geometry is the same. So it really takes a lot to do an actual validation. It's not just here's the data that put it together. So this takes a lot of time, and you want to match everything you possibly can. I'm not sure how else to, but you just try to match it everything you can. Shapes, we went through shapes. We took not only data at this place, and then all the data upstream. We tried to match all that to make sure it was also lined up. So we were pretty convinced we had this one nailed from that standpoint. Does that make sense?
Yep, thank you.
So Jim has next question.
Okay.
Thank you.
Slido.
Yeah. You can just ask it
Did you
out
do
loud.
Slido?
I did.
He did.
Excellent. Congratulations.
I think you made a comment somewhere that when you experience transition, you get a higher deflux than in the laminar vortex regime. Did I get that correctly? So I wonder what are the mechanisms?
Okay,
to bring that
I
about?
would expect a higher heat flux. Actually, what happens is when the heat flux, I don't have all the way. But actually, for the heat flux, I would expect to go up when the flow transitions. So the onset of transition, right? What actually happens is you get an overshoot in the transitional region. And if the different instabilities are trying to come into play, you actually get an overshoot in the transitional region before it settles down into turbulent. When it settles down into turbulent, the turbulent heat flux is going to be higher than the corresponding laminar heat flux. The
So
radius of the wall.
Is there some hyperconvection or something that's happening in the transition region that comes to?
The overshoot,
Yeah,
it's with all there are different modes that are coming in and they're the different modes. I don't remember the exact reason, but when we do an nonlinear analysis, we not only take like the fundamental, but we take the harmonics, all the harmonics and everything, you'll see in the mean flow distortion, and they all come in and interact. And I forget the mechanism that comes in, but one of them comes in and amplifies, and then it settles back down. But you can map it out, and then that's been observed is this advanced heat flux in the transitional region itself. But I just don't remember the mechanism. I have it. I could email it to you.
But maybe one more question and then we can shift it to the reception time.
I mean, it's not just like going from, okay, laminar to turbulent, but then in the middle, it also overshoots. And that's been observed.
Yeah, so Helen, you talked about that if your main gas edge is at an angle, you got a component that goes along the edge.
Yeah.
And that very much reminds me of like what you see in Delta Flyer, where although the angle is more steep on a Delta Flyer, and that causes the hook come up and roll over, if you will, on the wing if you're secondary roller. And that leads into its own instability mechanism. And I'm wondering if the instability mechanisms you see off of the delta wing and rolls off of those that cause them to eventually burst, if that would be relevant to what you're doing here as well.
You said on I couldn't hear the signal and
On
noise
a
about
delta
one up
wing?
here. Sorry.
Yeah, on a delta wing.
Delta wing. Okay. Yeah. Yeah. Where it
So
comes
they
up and
come, the
over.
rollers come in,
Yeah.
and then eventually when the angle gets high, the instabilities kick in and they burst, right?
Well, I need to get the rollover because of the pressure gradients occur. That's the mechanism there. But
But are
this,
those the same instability mechanisms that you see?
no,
on the delta
I
wings,
don't
or-
know. I don't think so. No, that's actually a vortex that gets created on the.
Oh, I
But
see,
somebody
I see.
correct me if I'm wrong. I
Okay.
think that's a vortex that just gets created off the wing, and then in itself, it's gonna have deflection points in it and everything that'll I think break down. But this is a smooth flow of the flow, down clear flow. It runs down the leading edge. This is just a snapshot of that. So it runs down and there's an instability. We model it with equations. This actually is unstable by itself. So unless you keep the leading edge radius small enough, with sweep angle small enough, there's a combination of the leading edge. There's a leading edge Reynolds number, attachment line Reynolds number. You keep the leading edge radius small enough, or the sweep angle small enough, in combination, then you can avoid this line and see. And that's what you do as a designer. You pay attention to leading edge radius and sweep angle. Usually that's leading edge radius, sweep angle. Does that make
Yeah,
sense?
perfect. That
Yeah.
totally answers the
This
question.
smoothly runs on here and runs back. Runs back along that favorable gradient.
Perfect, thank you.
Okay? Yeah.
We have one more that did come in on Slido from
Ooh.
anonymous. I don't know who it is. So what is your tunnel turbulence intensity? How did you define it? And what instruments did you use to measure transitions over your models?
The turbulence intensity is, again, I will have to defer to my computational colleagues as I get the, we're talking about here. The turbulence, this is a quiet tunnel, the turbulence intensity is, I believe it's 0.02% U infinity. And that's, I forget what the cutoff is, but the cutoff is such that the scales are all taken into account. I forget what the cutoff is with the bandwidth of the pass. I could email the information on that. And the way to measure transition depends on what the instability is. If you're measuring with the cross flow, I'm happy to get the tunnel details to whoever Slido is.
They're anonymous,
Mr. Slido.
but we can post it somewhere.
Okay, I'm happy to provide it. There are papers out there on it, but they do pay attention to we're aware that the scales, whether it's sound or vorticity will influence the algorithms. So really have to get all the scales involved. And I don't remember the particulars, but I can send you a paper. I'll send you a paper. Where was I heading? I'm heading through here. Okay, so in a swept wing, to answer the question about how you do transition location. Transition occurs on a swept wing where you see this the crossover vortices eaten away. And why do they get eaten away? It's because this thing, once those vortices get set up and get the inflection points, you get the secondary instability on here. Once this occurs, this is what's eating away the vortices. This streamwise instability, it grows so fast, the dynamic instability. And so once this is on here, that's what causes the flow, the vortices to break down. So how do you measure transition in a cross flow? What they do is they'll go across here and take kind of an average where the pattern is broken out. This is the transition interval. You can see it, but on the backs of the vortices, it's breaking down. That's a secondary instability. You just kind of take an average of this for crossflow. For streamwise instability, what they do is they'll take an instrument, a measuring instrument, and move along, and when they see the gap, sort of like a flight, when they see the amplitude or something, and all of a sudden start to look at amplitude, all of a sudden start to increase. That would be the transition location.
The person put their name in now, so now I can.
Okay, perfect. Did I answer that person's question?
Hopefully. Okay, but I know who it is now, so I can.
Okay.
All right, well, thank you very much. We'll go ahead and end it now. We've got.
Okay, thank you.
As a thank you for coming out here, we have a gift for you.
Oh, wow. Sweet.
Make sure you're all properly